All right, so can you guys see my screen now?
Yes, sir.
All right, so for the module 3, we'll talk about linear applications of op-amps. So as you guys may all know, there are two types of op-amps applications. So we have the linear, okay, and then the non-linear applications, okay. So for the linear applications, we have 7, and then for the non-linear, we have 5. So as you can see, we have already finished number 1 and then number 2, okay, which is the inverting and then the non-inverting amplifier. Okay, so we are now in number 3, which is the unity gain buffer, or sometimes you call this one voltage follower. Okay, so we will discuss them one by one, but for now we will talk about unity gain buffer or voltage follower for now. So just ignore the others to avoid confusion. So just focus on the number 3 for now. Okay, but before that, so let's just recall, okay, what is the open loop and then the closed loop configuration, okay, what are they about? So for the open loop, so again, this one indicates that there is no connection exists between input and output terminals of any type of circuit, okay, or any type of amplifier. So this is the open loop. So as you can see, our V out is as it is. Okay, it will not give a feedback to our input. Okay, so it doesn't have a connection or a feedback resistor. Wherein output signal will not give any feedback to our input signal. Wherein as a result, this will always give you a high gain. Okay, it's like 120 times or 1,000 times higher. Okay, like your 1 volt will become 1,000 volts. But then again, this one is unusable, okay, in real world, because having too much high loads or too much high gain is uncontrollable. Okay, it's not stable. Okay, so that is why we have the closed loop configuration. Okay. Anyway, before the closed loop, we have here the features of open loop. So again, yeah, it has no feedback, very high voltage gain, cannot be used as a linear amplifier, okay, because it has a super high gain voltage. And then this one is only used in comparators and waveforms distortions take place. So as you can see, waveform distortion takes place because having too high or too much gain can give you too much noise at the same time. Okay, so it has a consequence also, not only giving you a pros wherein, yeah, you're getting a high gain, but at the same time you're also getting a high noise, okay, or noise level on your waveform. Okay, so yeah, that's it for the open loop. And then for the closed loop, it has a feedback. Okay, so it's completely the opposite of the open loop, wherein it has a feedback resistor, as you can see right here. We have the RF from the output to the input in the circuit. So it is a part of output is returned or fed back to the input. So instead of having all the outputs in here on the V out, okay, some of them will go to our inputs, okay, or to our uh, inverting input. Okay, so this is our V in, and then this is our inverting inputs. So it's like dividing the total uh, gain of this certain amplifier. Okay, so the benefits of having a closed loop is, of course, it's like just completely the opposite of this one. Okay, you will get uh, oops, low voltage gain, but in return, you'll get a stable and more controllable voltage. Okay? So this can be used, of course, if you have feedback, this can now be used as part of the linear applications, okay, or linear op-amps. Okay, and then at the same time, it will not give you, or it's not susceptible to waveform distortion, because only gives you a smaller, so yeah, not really smaller, so it's still high, okay, but it is now controllable and lesser distortion of waveform. Okay, and one more thing, we have here the types of feedback. Okay, so Maybe you guys already know this one. But we have the positive feedback or the regenerative feedback, and then we have the negative feedback or the degenerative feedback. So this one is actually like saying that if your input is positive, then you must also get a positive output, right? If the case is like that, then we call that one positive feedback, or it is in the same phase. Okay, we are in line with each other. Okay, positive, positive. However, if you say you have a positive input and then you have a negative output, we call that one negative feedback or the generative feedback, wherein it's 180 degrees out of phase, meaning it has the complete opposite of your original waveform. So originally, let's say you have a positive waveform, but your output will give you a negative waveform. Okay. So those are just the types of feedback that you will get out of an amplifier. All right, so this is just a recall. Let's now move on with our main goal for this module, which is the unity gain buffer, okay, or sometimes call this one voltage follower. All right, so is there anyone here who has an idea what is voltage follower? Where do we use such circuit or amplifier? Anyone? Hello? You guys still there? Ako iniwan na ako. Wala nang tao.
Dito pa kami, sir.
Hindi pa ba kayo? Okay. So, sa main chat, nawala yung chat. No idea, sir. So, no one here has an idea about voltage follower. Walang idea, sir. Okay. So, supposedly, I will not give this one as your laboratory since this one is quite useless, actually. Okay. But not in terms of I can disregard it and then not learn what is voltage follower about. Okay, so as you guys may all know, going back here, an amplifier, just from the word itself or just from the name itself, it amplifies the signal, right? So having a low voltage or low input and then having high output or high gain. Okay, but in a unity gain buffer or voltage follower, okay, it doesn't do anything with your uh, inputs or with your signals. So whatever is your input, it will give you the same output. So it's 1:1. Okay? It will not do anything. So that is why in voltage follower, V out is always equal with your V in. Okay. And then this one is gain with feedback. Yes, this has a feedback or a closed gain of this circuit is 1. Okay, so you will know later on why this one is 1. And it is a special case of non-inverting op-amp. Okay, so take note, special case non-inverting op-amp. So this is really super special because it's under amplification or amplifiers, but it doesn't amplify your signal. Then, of course, this one is similar with non-inverting because your input is on the non-inverting side, and then it also has this feedback resistor. Okay. But then again, it's an special case. Okay. So therefore, in this circuit, the output signal is in phase with input signal. So how do we know, or how did we know that the output signal is in phase? That's because your input is in the non-inverting. So can you guys still remember? If your input is in inverting, you have a positive input, it will become a negative output. But for the non-inverting, whatever is the sign of your input, it will not change anything. Okay, so it will stay as it is. So yeah, it's in phase. Okay. So feedback resistance, uh, RF is equal to 0. Okay? And then R1 is equal to infinite. Okay, that's their default value when it comes to having a voltage follower. Okay, so that is why if ever you're going to use a formula later on, which is it in here? Yeah, it's in there. Okay, you will get the same input or the same output. Okay? It's always like that the case. So B in is equal to B out. Anyway, here's the voltage follower circuit. So we have here the R1 and then the RF, and then of course this one should be grounded. And then we have here the voltage input, okay, which is connected with the non-inverting input. And then we have here the outputs. So as you guys may all know, this one is virtually short circuit. So what do we mean by virtually short circuit? So initially this one, positive and negative, it's like they are not connected with each other. But in reality, they have or they are connected, which is we call virtually grounded. Okay, because of course this one has a loop wherein this one is grounded, this one is also grounded, so they now have a connection in a way that they are virtually short circuit. Okay, so we have here the R1, okay, wherein it is always equal to infinite, and then your RF is always equal to 0. Okay, so since if you can still recall, since an amplifier always try to make the input on the non-inverting and then to the inverting, it always make the inputs equal with each other. Okay, so that's the minimum rules when it comes to amplifiers. So it always try to make this input equal with this input also. So if you're going to take along this one, uh, V2 is equal to V in, okay, which is your voltage input. And then going back to the rules on our amplifiers, since V2 is equal to V in, V2 must be also equal to your V1, which is the voltage input of your inverting. Okay? So that is why you could say that V1 is equal to V sub 2 is equal to V sub in. All right. And then that is why whatever is your input, we'll just go back here. And then if you're going to solve this one using this formula, you will get this result. V sub O is equal to V sub E. Okay, so here's the computation. So the output voltage follows the input voltage. That's the reason why we call this one voltage follower. So in other words, V out is equal to V in. So here's the formula. Okay, so this one is just a simple formula for getting the gain for an amplifier. So 1 plus RF divided by R1, wherein R1 is infinite and then RF is 0. So if you're going to do the math, okay, you will get this one. So 1 plus 0 divided by infinite is equals to 1 plus 0. Okay, so this one is actually just 0. So nothing's happened. Okay, thus having now only 1. Okay, so your gain is just 1. Okay, so as you can see, it didn't amplify your voltage input. So whatever is your voltage input, it's the same. It's just going to be multiplied by 1. Okay. So what else here? So since P out is equal to V in, voltage wall doesn't provide any implication, which is this one. So this is just another continuation or expansion of explanation. But just from here, you could already see that AF is equal to 1. Okay. So that is the reason why a voltage follower doesn't do anything. Okay, so as you can see, it's quite useless, right? Because why would you uh, input a voltage in here if it will not do anything with that voltage? So it's like just a wire, okay, that just passing through on that certain wire. Anyway, we have here the reasons on why we're going to use such circuit. So reasons for using a voltage follower. So it has also an importance. So a voltage follower does not increase or decrease the amplitude of the input signal, and it does not filter out high frequency noise. Thus, you might be wondering why a circuit like this is so useful. Okay, so it says here this one is useful. It is true that a voltage follower that does not intentionally alter the amplitude or frequency characteristics of the input signal, but it does allow us to improve impedance relationships. So, going back to the Ohm's law, as you guys may all know, when it comes to Ohm's law, uh, the more load or the more resistors that it will pass through, the more that your voltage or the more that your current will decrease, right? But in voltage follower, okay, it neglects, like it's like removing the noise level, or instead of having a voltage drop, okay, on each resistor or on each load, okay, it will not uh, lessen or decrease your voltage input. In fact, it will maintain it. So you can say that this voltage follower is a maintainer of our voltages. Okay. So whenever we are sending a voltage signal from one subcircuit to another, we have to consider the output impedance of the source subcircuit and the input impedance of the load subcircuit. Okay. Thus having a lower uh, voltage output. Okay. So the source's output impedance and the load's input impedance form a voltage divider. Okay. And consequently, voltage transfer depends on the ratio of input impedance to output a certain impedance. So this one is effective voltage transfer requires a source circuit with low input impedance and a load circuit with high input impedance. So meaning, to make it short, it neglects the voltage drop and then it still maintains the voltage input. Okay, so just by applying voltage divider, okay, so we can control, okay, so we can control the voltage output that we wanted. So for example, we have 5 volts. We want to control it to make it 3 volts, or we want to control it to make it 4 volts. So we can do it just by applying a voltage divider. Okay, so it's like actually the main use of a voltage follower. So it is always uh, intact with a voltage divider. So it's not just like a voltage follower circuit. It also has a voltage divider circuit in it. Okay, so take note on that one, because in that case you will be able to control the voltage output. But however, okay, since this one is just only maintaining the maximum, so whatever it can provide, let's say 5 volts, then it can only provide 5 volts also. It cannot provide uh, higher than that, like 6 volts, 7 or 8 or 9 or 10. Okay, so you can control it below, like 4 volts, 3 volts, 2 volts, and then 1 volt, but not higher than 5 volts. Okay. So here are the other reasons wherein with the use of voltage divider. So a voltage follower has low output impedance and extremely high input impedance. And this makes it a simple and effective solution to problematic impedance relationships. So if a high output impedance subcircuit must transfer a signal to a low impedance subcircuit, a voltage follower placed between these two subcircuits will ensure that the full voltage is delivered to the load. Okay, so one example of this one is this simple circuit. Okay, so it's a voltage follower wherein we have here a voltage divider. Okay, so it's a combination of those two circuits. Okay, so knowing that one, okay, I'll give this one to you as your laboratory number 10. Oops. This is number 10. Yeah, there you go. So this is your 10th laboratory. So I would like you guys to create a voltage follower wherein it will only give you an output of 50%. Okay. So design a voltage follower with a voltage divider on it. assuming that you have a 60 volts input voltage with a frequency of 60 hertz. So create a circuit wherein it will only output 50%. So I guess this one is super straightforward. So 50% of the original input voltage. So take a screenshot of your schematic and graph of the V in and V out. Okay. So I would like you guys to create a circuit wherein it will only output 50%, 80%, 20%, and then your reflection or conclusion on the circuits that you have accomplished. So from those circuits or problems that you have accomplished, what are your thoughts about voltage follower? So what are the benefits of it in our circuit industry? So why do we still use such amplifier or linear applications of amplifier? So give a scenario on this one. Okay. So we have 4 questions under voltage follower. So again, as I mentioned a while ago, it cannot amplify, but you can control the voltage output. So I'll let you guys read this one for 10 seconds. And then verify it one by one. And then you might have a question. So all of those are the same circuitry, just a different output. All right, so is your 10th laboratory clear so far? Or you're confused? No? Are you guys still there? Percentages. Okay, so what is your question about percentages, Mr. Pacific?
And I'm not understanding the role of that percentages. How are we implement percentages?
So, because you're the one who's going to create the circuit, right, Mr. Pacific?
Yes.
And then in creating that circuit, of course, you're going to have a voltage divider, as I mentioned on the uh, instruction. Okay, so voltage follower with a voltage divider on it. Okay, and then if you're going to take a look on the example in here, this simple circuit, we have here resistors. So
Mm.
those are the values, okay, or those ohms or resistance are the one that you're going to control or change from time to time to have an output of 50%, 80%, and then 20%. So what is the 50% of 60 volts? So I'm expecting 30 volts output. And what is the 80% of 60? Okay, so I should see 80% output on your circuit. And then what is the 20% of 60? Okay, so I should see 15 volts of output. Yeah, is it 15, 15, 30? I don't know. It's 12, not sure, but uh, 60 times 0.20, and you will get that output.
Okay.
Right. So this one is actually quite simple, since you guys already know have an idea what is a voltage divider. This one is like a bonus already. 10 A, 10 B, and then 10 C. So you might need some trials on how to come up with the 20% V outs. Any other questions or clarifications? So is it okay now? Or would you guys like to take a look on your or take a look on this one more for 1 minute or for 2 more minutes? Well, anyway, so yeah, I think that uh, you're having a hard time in understanding this one because maybe this is your first time in uh, having a problem and then solving it by creating a certain circuit on the auto spice. Because before, of course, as a starter, as a beginner, I gave the schematic and then I gave the values of that schematic. And all you need to do is, do it, copy it, and then just run it, and then just uh, get the graph of the V out and then the V in, and then take a screenshot, and then that's it. But for this one, so you have to analyze this one a little bit more. Okay? So let's say that this one is a little bit more harder. Well, anyway, so we cannot stay here forever. So that's it for your 10th laboratory. If ever that you have a question or a clarification in the future, as long as you're not asking on how to do it step by step, then I will help you. Okay. So sorry for that one. Anyway, so let's now proceed to the next one. So after the unity gain buffer or the voltage follower, so we have here the voltage to current converter. Okay. So what is this voltage to current converter? So as its name implies, it converts the voltage or the voltage source into a current source. Okay. So why do we do this? Because voltage signals in a parallel circuit may vary from one to the other due to resistive wire losses. So as you guys may all know, voltage always um, has a voltage drop when it comes to passing a wire or passing a resistance, okay, or a resistor. Okay. But for current, okay, current sensing instruments typically have low impedance, while voltage sensing instruments have high impedance. Wherein, if we have a current source, okay, this one has a greater electrical noise immunity, meaning there's a lesser chance that the voltage or the current itself will not slowly degenerate. Unlike for the voltage source, so the longer the distance or the longer the wire, the more voltage that it will drop as it goes to its destination. But for the current, okay, it's stable. Okay, whatever's the current on this wire is the same with the current on the end of that wire. So that's the benefit of having a voltage to current converter. Okay, so here's the solution. So we have to convert this voltage into a current source. So that is why we have this V to I conversion. Wherein in this V to I conversion, we have this circuit. Okay, so let's say this one is a TV or a display or any device. Okay, so to avoid voltage drop or voltage loss, okay, so we have to convert this voltage into a current. So uh, one benefit of having a voltage to current converter here is the It does not matter what resistant value our load is or how much wire resistance is present in that large load. So long as the op-amp has a high enough power supply voltage to output the voltage necessary to get 20 milliamps flowing through the R load. So this 20 milliamps is only specifically on this circuit. So as you can see, we have here, let's say, a 5 volts or ranging from 1 to 5 volts input. And then if we have 1 volt, of course, you will get 4 milliamps. And then if we have 5 volts, then we will get 20 milliamps. So how did we get this one? Just by using this formula, which is I is equal to V divided by R. So V is, let's say, 5 volts. And then your R load here is, or your R here is 250. So 5 divided by 250, you will get 20 milliamps. Okay. If you have an input of 1 volt, then you will get 4 milliamps. Okay. And so on and so forth. Okay. Depending on the values of your resistors. So it doesn't matter if we have here an R load or a resistance of 1000, 1500, 2000, as long as we have enough high power supply. So while waiting, do you guys have a question or clarification? So don't be shy to ask. Answer coming from Mr. Eda. How about the others? Do you guys have a question? Answer.
None, sir.
Answer.
All right. How many are we during the part one? Because I think we were only 18, but right now we're now around 20. Is there anyone you have noticed? How many are we on or during the part one?
23, sir.
Three. So there's three more. Mhm. All right. So I don't know if they're still going to join us. Anyway, so we're almost done. Actually, I thought we can finish this one in just around 30 minutes or 35 minutes. I was wrong. Anyway, so here's the solution for us to have a stable source. Okay, so instead of having a voltage source, we're going to use a current source. Okay, so just use this formula and then you will get the uh, source, or the milliamps that it's supplying under the R load. So let's see in LT Spice if we can do this one. Oops, English schematic. So one thing, okay, so one thing that you have to take note under voltage to current converter is you must use a specific amplifier. Okay, so let's discuss this one now. So in order to use current as an analog representation of a physical quantity, so we have to have some way of generating a precise amount of current. Okay, so there's a lot of op-amps wherein they have their own specification and own purpose, but we have this certain amplifier wherein it's specifically made for a voltage to current converter, wherein it must have a precise amount of current within the signal circuit. So why precise amount of current? Because the one that we're going to use now, or the one that we're trying to output, is the current source. Okay, so we don't care what is the voltage source anymore. Okay, what we care is the current source. As long as we have a consistent and precise amount of current, then we're good to go. So just look onto the LT Spice, the OP07. Okay, so you will see here it's a precision operational amplifier. Okay. So the same schematic, we have the real voltages here, the inputs, the inverting, non-inverting. It's just that this one is programmed uh, for more precise amount of current, right? Okay, so let's now try to recreate this one. So let's see if we can get the same result. So go to the components and then op amps, and then look for the OP07. So letter O, there you go. So it's OP07 or OP07. So just get that one, and then I'll create the real voltages first. So one here and then another one here. So you can use this one, okay, or you can use this arrangement. But if you're going to use this one, positive going to negative, so you have to indicate that it's negative. So you have to put negative something value. But if you're going to use this one, so this one now is understood that you're supplying negative to negative. Okay, so we'll just use this one. So to not include a negative sign anymore. Then of course, it must be grounded side by side, and just connect this one on the real voltages. And then we have here a feedback resistance, or in voltage to current conversion. This one now is R load, and then we have here the R1. Okay, this is the R load. This is the R1, which is also grounded, of course. And then we have here the voltage input, which is also grounded. All right, so we're now done. So by default, this one is 250. Oops, 250. And then we have here a voltage input. So instead of having a DC value, okay, so we'll use AC. So go to sign, and then I'll use 5 volts, and then 60 volts. So I'll just move this one right here. And again, this real voltages are our power supply, wherein it can supply up to positive and then up to negative values. So we'll just put here 100 volts to avoid complications. Okay. And then 100 volts. So as you can see, I didn't include a negative side anymore, since we have this kind of implementation or arrangement of voltage source. And in here, so for now, we'll start with 1 ohms, and then we'll see if there is a difference, no matter how high or what is the value of this resistance. So take note, this is your R load. And then this is just R1. All right, so let's now simulate this one, 50 milliseconds. So of course, initially we have here 5 to 5 volts, peak to peak, 5 to -5. And how about our output, current outputs? So once you see this one, just left click. So as you can see, we have here an inverted result, okay, for your current. Oops. So in here, we have a maximum of negative 20 milliamps. So take a look on the right side. This one is for the milliamps, and this one is for the voltages. Okay. And if you're confused, then you can just double click this one. So as you can see, we have a peak-to-peak negative 20 milliamps to positive 20 milliamps. So are we getting the same result? So yeah, as you can see, we have here a result of 20 milliamps. And then why negative? Because as you can see, the polarity of your circuit now is something like this. So positive going out here is still positive, but once it passed through this R load, your uh, current here will become negative, okay, due to the polarity of your R load. Okay, and then let's see if there are changes. Let's say we would get a higher resistance, say 100 ohms. So as you can see, no changes. Okay, still have the same negative 20 to positive 20 milliamps. Right. How about if it's 500 ohms? So there's still no changes. Okay. So as you can see, oops. So as you can see, it does not matter what is the resistance value of the R load. Okay, as long as you have enough supply on your amplifier, then it will give you the maximum uh, input, okay, of your voltage input or voltage source. So 5 volts, it can provide up to 20 milliamps. So any question or clarification so far regarding voltage to current converter? Right, so none. So in real life, maybe you're wondering where do we use this one? So in real life, okay, so we control some devices using current. So actually, either of those two, it could be a voltage or current. So you can power up any device. But in real life, okay, so maybe this is where you're going to connect such loads, like for example, your television. Okay, so as always, you will get 20 milliamps in here of current, okay, or electricity in having this kind of circuit. Right. So that's it for the discussion, and then we have here your laboratory number 11. Okay. So this one now is for the voltage to current converter with floating load. Okay. So this will be your research work. Not actually research work. Research assignment. Okay. So you have to search for the circuit, okay, or schematic of a voltage to current converter with floating load. So in a voltage follower, we have the voltage divider, but in here we have a floating load. So what is the schematic of the floating load? So we have 3 questions in here. So for the first two, okay, 11A and then 11B, so the only difference is the in phase and then not in phase. Okay, so again, if it's in phase, whatever is the input, it should output the same waveform. So positive, positive also. But if it's not in phase, so it's the opposite. Okay, so it says here, design a voltage to current converter with floating load, assuming that you have a 10 volts input voltage with a frequency of 6 hertz. So set the resistor value on the inverting input of 50 ohms. 250, I'm sorry, and then create a circuit wherein it will output the same phase of the original input voltage. So use the proper amplifier on this. So you guys already know what I'm talking about on the proper amplifier. So do not just use the universal op amp. okay, or op amp or op amp 2. So you have to use a specific amplifier for the voltage to current converter, which is the OP07. Okay, this one. Okay. And then, so which is designed to work as a precision operational amplifiers. And then take a screenshot of your schematic and the graph of the V-in and the current of the load. So before, you're only getting the screenshot of the V-in and V-out, but in voltage to current converter, of course, you're going to get the voltage input and then compare it with current, okay, or current load, just like what we did in here. So you get the graph of the R load or the current on the this resistance. Okay, so design with in phase and then design with out of phase. Okay, so those are the only difference. And then for the second to the last, we have here a voltage to current converter with ground load. So if we have floating load, we also have ground load. So what is this ground load? So I would like you guys to search on the internet what is the schematic of the this 1 voltage to current converter with ground load. So basically the same. We have 10 volts input, 60 hertz frequency, and then it's just that in here you have to set all of the values of the resistors to 250 ohms, except the R load, which is equal to 100. So everything is 250, and then R load is equal to 100 ohms. So again, we use the proper amplifier on this, which is designed to work as a precision operational amplifier, and then take a screenshot of the schematic and the graph of the in and current of the load. Okay, so only one question for the ground load. And once you're done with those three, so quite similar with your laboratory number 10. So from those circuits or problems that you have accomplished, what are your thoughts about voltage to current converting? What are the benefits of it in our circuit industry? And then give a scenario. Right? So that's it for laboratory number 11. Any clarification so far? So the one that we have in here is just a normal voltage to current converter. Okay, this is the default one. But we have another two types wherein it's really usable, or really the one that we're using in terms of in industry. So we have the floating load and then the ground load. Okay, so I would like you guys to search on those or the schematic of those, and then do it as your laboratory number 11. So any concerns so far regarding with your 10th laboratory and then 11th laboratory? Okay, so none coming from Mr. Escobar, Mr. Adam, and Mr. Martinez. So maybe for now, I'm not the one who's assuming that you guys do not have a question. But in the future, as the time that you're going to create those schematics, so maybe that's the time that you have a lot of questions. Okay, so good luck in finding those answers, since maybe this is your first time in encountering this kind of problems. So again, before it's super easy in midterms, but in finals it's now really quite difficult. So you have to know the concept of a certain amplifier. Okay, so okay, that's it for the laboratory number 10, and then 11. So if you guys do not have a question anymore, then you guys may now go. So I will just upload this one on our Facebook page. Okay, so thank you too, and goodbye. Thank you for coming. Goodbye. Thank you and goodbye. Goodbye. Bye bye.